A wheel of radius 6 centimeters and a radius of gyration of 5 centimeters starts from rest and rolls down a slope. What is the linear speed when it reaches a point 40 centimeters vertically lower than its starting point? So this thing rose up to somewhere here, where if we measure the vertical height, it's giving us 40. Now, what can we do from here? Well, we know that it is coming from rest, so we can use conservation of energy. At this point, it only has potential energy, it's not moving. So as it gets to rotate, the energy is going to be converted. By the time it reaches this point where it has just rolled for just 40 centimeters in the vertical, the whole potential energy is going to be converted into kinetic energy, but because it is also rotating, it also has rotation kinetic energy. So the potential energy is given by mgh, kinetic energy is given by half mv squared, and then plus rotation kinetic energy is given by half mass. The equivalent for mass is inertia, and then we have got now the equivalent for velocity in rotation terms, that is angular velocity squared. So here we've been given two radii. We've got the radius of gyration and just the radius. So I'm going to break down. We know that moment of inertia, I'll write that in another color so that we get to differentiate. Moment of inertia is given for a wheel. The moment of inertia is simply mr squared. So that will be mr squared. And now we know that angular velocity is the same as linear velocity divided by the radius. So in this case, because it's squared, we are going to square those two terms. That will be linear velocity squared divided by the radius squared. Now this radius is different from this one. So the radius of a gyration is the radius that is taken from the very point where the mass of an object is concentrated. In other words, where the moment of inertia can be calculated from. And therefore, when we are using the radius in the moment of inertia, we use the radius of gyration. Now this radius is simply the radius of the point just from the center to where the end is. So when you've got a wheel, the radius of gyration is not always equal to the radius of the wheel, but most of the times you take them that they are the same. So because for some objects which are not fixed, the radius of gyration, just which point is the mass concentrated. So the point where the mass is concentrated, and then to the very end of that something, that will be called the radius of gyration. So now we can see that the masses are the same throughout, so the mass will be able to cancel out, and we're going to remain with gh is equal to half v squared, and then plus half, we have got r squared. Remember this r which is here, the r we are using in green. Let me still write it in green, and then multiplied by now velocity squared divided by r squared. So now I'll go on and substitute my values. The g is 9.8. The height, when it has fallen for 40 centimeters, and 40 centimeters is the same as 0.4 meters, divide that by 100. That will be equal to half. We don't know the velocity squared plus half. This r in green is the r that you've substituted on the moment of inertia, and so we use the radius of gyration, and the radius of gyration has been given as 5 centimeters. Converting that to meters, just divide by 100. That is going to be 0.05, and that is squared. And then multiply by the velocity squared divided by the radius. Now this is simply the radius of the wheel itself, and that is 6 centimeters, which is 0.06 in meters. Also square that. So let's get to multiply 9.8 multiplied by 0.4. That is a 3.92, and that is going to be equal to 1 over 2 v squared plus. So here I'll get first a 0.05, square it, and then I'm going to divide by the 0.06 squared. The answer that I get, I'll multiply it by a half. So that is giving about 0.3472, and then we have got the velocity squared there. So it says 3.92 being equal to, so I'll add now this plus 0.5. Of course, half is a 0.5, so I'll add that. Because these have got all v squared, those are like terms, that's why I'm adding them. So we're getting 0.84722 v squared. Now to remain with v squared, I would divide both sides by 0.847, and that is going to give us v squared being equal to 3.992 divided by 0.8472, that is 4.626885. So to remain with v, I'm going to take the square root on both sides, and that is going to give us 2.15. This is in meters per second. So this is the velocity at which it was moving when it reached this point. Now for the second one, that is part B, how fast is it rotating in revolutions per second at that point? So we just need to convert this velocity to revolutions per second, or in other words to angular velocity, because it's linear velocity. We know that linear is simply angular multiplied by the radius. Therefore the angular is going to be the linear divided by the radius, and that is going to be equal to 2.15 divided by the radius. Now this is simply the radius of the wheel itself, not the radius of gyration. So the radius is given as 0.06, which is 6 centimeters. So that is going to give us, divided by 0.06, that is 35.85. Whenever we divide linear velocity by radius, the velocity we're going to get is always in radians per second, but we want it in revolutions per second. So what I'll do is I'll simply write this, that 5.85 radians per second times, I want to have revolutions, so I'm going to take radian down and then a revolution on top. I know that in one revolution we have got 2 pi radians, so the radians and the radians will cancel out. So 35.85 divided by 2 pi, so that is given me 5.7057, which we can as well write as 5.71 revolutions per second. So that is it for this video. Thank you so much for watching. Enjoy your day.